Can you see my screen?
Yes, sir.
Yeah, okay. Yeah, I just wanted, to start by asking a few questions just to see if you guys are following the lectures. And first of all, thank you for accommodating me with these online lectures late in the evening. So let's keep it. I know it is late in the evening for you after a long day, I'm sure, and you must be a bit hungry as well. So I'd appreciate your thing. So let's keep it interactive. I'll, ask questions every now and then to see if you're, uh, on top of things, if you're following what I'm saying. So you've seen this example. I want to keep these slides side by side. So I hope you can read it. I'm not going to go, I'll go eventually to full screen mode. But since I imagine that all of you are looking at the screen, this is not too small. You can read it, no? In this mode. You
It's
are.
fine, Professor.
Yeah, okay. So you saw this example, I mean, that I showed for this the mutex example, two process mutex example, for which I constructed this transition relation for this system, this multi-threaded asynchronous process. And the transition relation is defined by the first line, okay? Assuming that the transition relation for each of the individual processes, the threads or process is constructed as shown by the formula, the disjunction, the five disjunct formula here, where my cursor is, then what I call as the global transition relation for the asynchronous composition is denoted by the formula on the first line. Okay. So after constructing that T, so that's what I denote as T, and I have not shown the initial. There's init also. So that's the transition relation, and the init is also defined here in the first bullet. So once given that is the transition relation, this formula is the one that is defining the translation, then bounded model checking really does what is shown here on the left side. Okay. So the first line of this formula, where my cursor is what I call as a BMC formula, BMCK, okay? And E is the part in the BMC formula which checks if there is an error. So, so in this context, my first question I'm asking is, what does the first part of the formula denote?
It denotes init and also it denotes the trace from x0 to xk.
Yeah, I want a more intuitive explanation. So, what does that execution mean, or something that satisfies this in terms of this process, this combined process run? What does it indicate? It indicates, yeah, a k long what? A k long. Obviously, it is indicating a k long. What is my question? In what sense is it capturing the behavior of this concurrent program? that first part. I mean, the reason is important is because if this is fails, okay, if it is satisfiable, then it means there is an error, right? So I want to make sure that you understand what in what sense is there an error, okay? When this formula, when you ship it to Z3, if it comes up with a SAT, that means that there is an error, right? So why? Okay, I'm trying to get at that thing to see to see if you understand that. Okay, okay. Since
I mean, do do you mean like reachable states? I'm not sure. I mean, the X, they're all
yeah, I
reachable,
mean,
and
well, it is more than just reachable states because see, as I've been repeatedly saying, this first part, like Lucky kind of said, I mean, he was a little bit too pedantic. I mean, not very intuitive. So this represents a, a trace, right? That's, I mean, I wanted, okay, so a trace means some sequence of a run starting from an initial state, right? So anything that satisfies this. What does each step in this trace represent? It is so another way of saying is it is some because each of these things, each T here represents a step of the global combined process, right? So, for example, I mean, what I showed here is this what I call as the global transition system. Okay. Why? I mean, sometimes it's referred to as a global transition system because you can have a transition a system for just the individual process, each of these things. And here it is, what is this global transition system denoted here as a graph representing? It is the interleaving, all possible interleavings of atomic actions in each of the process, okay, of each of the process. Okay, I mean that is the answer that I was expecting. Now is that clear? So that is why, because anything that satisfies the first part here is some interleaving of the atomic actions of the individual process, which is what you expect the behavior of a in a synchronous composition, parallel in a synchronous parallel composition of these two processes is okay. So in that sense, yeah, that is what I was saying. So any possible interleavings, because these things can be scheduled, the context can be switched at atomic action boundaries, and therefore this way of modeling this transition relation, it corresponds to sequences of different interleavings, and whatever property that you wish to prove, if whether an invariant property or a liveness property, is expected to be true for all traces that feasible traces that is a solution to the first part. The second part says yeah, here, for such systems in parallel compose, parallelly composed multi-threaded things, the kinds of property that you want to prove are all global properties. They are stated on the global state. By a global state, I mean it is the composition of the states of each of the process, the two processes here, and that's what is being denoted in each circle here. And E, if it's an invariant property, it just says something like here, what you something bad should not happen, or it is the negation of something that negation of what you expect to be good. So, and here it's ensuring that if E here denotes the error state, so it is checking if there is a if there is an error in any one of the states on the feasible trace of this global transition system. Okay, is that clear now? Okay, so so these, yeah, it's a mouthful, but that's how it formally, and that's why I mean, the important thing is that this BMC formula represents a K long a trace of a feasible a legal trace of the global transition system, representing the parallel composition, asynchronous parallel composition of these two processes. So that's what I wanted to make sure. So any questions there? Okay. Now, so here in this slide, I say it can be checked like this or like this. Okay. There is a small point that I forgot to make last time. So the formula here above, given any trace, K long trace, it checks if if this satisfiable, it means that it checks that there is a violation of the property, or there is a violation of the property in any one of the up states up to in the K long trace. Now, if you're doing it incrementally, that is, if you're doing it first checking for traces of length 0, length 1, length 2, etc., then what you don't need to each time test for every state starting from x0 to xk, because each time you are testing at zeroth step, you're taking ex0 at, and you would run the next BMC check with K plus one only if you ensure, I mean, only if you don't have an error, if the previous step is an unsat step, okay? And therefore, at any particular ith iteration of the BMC checking, this is what sometimes is called BMC is incremental, because K is being incremented each time by one. You don't need to test for all of it, because you would move to the K plus one step only if there was no error. Okay, that is, the formula was unsat. Okay, in the previous step. So then you could just, okay, to test this an E, whether an error occurs in the kth step. Now, Ayan, you did say reachable state. Yes, you were correct. Okay. So that was like a partial answer. Yes, this one, the last state in this BMC formula, XK, does represent the all possible states that are reachable in K steps. It is true. So in each thing, it is true. But as conjunction of this, it represents a trace starting from an initial state. Okay. Now, so that is well and good. And this seems like the right way to model for a concurrent systems. Now, let me, go to a sequential. So I'm going to raise a question, which I did in the last class, but I'm going to do it anyway. So take this example, a sequential code. Okay, that, as you know, is being modeled by a transition relation here, and we have added a component, a PC component, which At any particular point, you are in one of these PC locations, okay, starting from entry to exit. So here, what does, once again, I ask, what does TSS prime? Like I said, TSS prime in the concurrent system, it represents an atomic action, okay, from one of the process. What does TSS prime represent here? Anybody?
Transition.
Yes. In terms of program execution, what does it represent?
I
Like the
mean, I
program
am at
counter is changing
Yeah.
something, like there is some change of the program counter is.
More precisely, I mean, why is this? Okay, I've written a big formula here. Okay, what is this formula saying?
that if I am at a entry line, if I am at PC counter entry, then my next PC should be L1 and all. That I am. Uh,
Yeah, but it's not only saying how the pieces remain, it's telling what exactly happens. Okay, the effect of executing the
yes.
instruction at that PC, right?
Uh,
Because your
yes.
program, it is relying on the fact. So in effect, it is saying it is modeling the effect of executing at one instruction of the program at any point in a full execution, right? Starting from entry to exit. Since you're in this while program, it also produces a trace. And here it is, and since you know that your PC can only be in one of these set of locations in the program, and that's how we have captured PC. We limited PC to be something between entry and an exit, both sides included, and therefore it is representing. So, I mean, a precise way to say is it is capturing the effect of executing an instruction in the program when the control is at a particular location. So including what the next program location is as well. And that's why in a way it you could say by repeated execution of this in a BMC formula, it gives a trace of starting from a k-long trace, a feasibility k-long trace that starts from an initial program. Now, the point that I raised in the last class, I'm repeating here, for the people that are here, I mean, who are not there, is that I'm raising the question, is this the best way to model? Okay, so in the case of a concurrent system, all my properties I wanted to state on the global trace. Whereas for sequential program, mostly what I want is it is the specification, while you could view it as property on these traces, normally since there is only one thread running here, the specification of interest is usually expressed as if there is some assumptions I make of the inputs, then when I exit the program, you want some condition to hold good. In this case, for example, you would expect that when I exit the loop, y is always even, right? Because it starts in a state y is equal to 0, and every time it is incremented by 2. And if this program ever exits, the value of y would be 1. Therefore, I mean, would be even. Therefore, so yeah, and the reason that I say, a lot of people feel that this way of representing is now, if there are, so for example, you have, T represents one instruction execution. Therefore, how many steps of T do I need to execute in order to, since I'm interested only, I mean, mostly I'm usually interested in checking a property when the program exists, just imagine how many, but this is too low level, one can one can say. So in order to ensure, I think how many steps of how many steps, what is the k that I would have to do, because it is, of course, that depends on when what the initial value of x is. But the point that I'm trying to make is this is too low level. And here, for example, you may want to measure these things, since what you're interested in are paths, and and these paths are usually here generated, at least the unbounded paths here are generated using loops, and therefore you may want to express, okay, I mean, this way is also fine, but what it says is all possible if you have a transition relation like this, and if there is k unrolling of that t, it says if there is ever a way to exit the program in in up to k steps, it'll check for all those traces. Okay, yes, it does that, but might it not be better to actually, instead of having the PC and then don't, because but here it also models all the other way. I mean, in the T, you are also including, and in your unrolling, there'll be all other parts which never get, will never get, for some input value, will never get out, will never exit the loop. Therefore, the point is, the question people started raising when they, people who used build verification system, won't it be better to enumerate what I call symbolic paths generated by this thing, instead of making this k copies of t, which represents all possible paths that are generated in k. Lot of it may not even reach the exit point. Why not? Could you not have a much leaner formula if you were to enumerate the paths, what I mean, the possible paths from the initial state to exit, from the exit point, model those paths, those set of paths, and then directly represent them. I mean, as formulas, and solve them. Okay, that is the point, that would result. Maybe that would result in a formula that is much smaller than modeling the entire program. Now here, this was small enough. Just imagine if your program had nested for loops, where the body had all kinds of nested if then else's. This T will be so huge, and only when you run it for k steps, only a very small part of the paths that are represented from there will even make it to exit. Instead, the question that verification tool builders were raising was, why not enumerate the paths, okay, and then model each of those, and model your behavior as a set of paths. And that is what was was the motivation for this example here on the left side. I mean, what does it mean to enumerate? I'm saying, of course, you can't enumerate all parts. Otherwise, you'll have to enumerate what I call as symbolic parts. And here in this example, this represents what that means. Okay. So basically, see, this is a program. This is a straight line program. Has nested if then else. So a symbolic path is defined by a combination of all possible combination of truth values for the conditions, for the branching conditions in a program. Okay, it is defined by that. So, for example, here, as I said, there are these are the three possible combinations, the truth values for how these two branching conditions can take. The first one is where both of them are true. The second case where the first condition is true but the second is false. The third is where the first condition itself is false. Now, why do I call this symbolic paths? Because notice that each of them represents a set of actual execution runs. Okay, because the initial values of m and n here are not specified. It could be anything. So each symbolic path represents a set of actual execution runs in a simulation, potentially infinite number of runs, and therefore you enumerating paths like this, since you're enumerating symbolic paths, still it'll only be finitely many paths that are possible, symbolic paths, and the hope is that there'll be small number of them, and therefore now here each of these, once you enumerate this way by looking at one for every combinations, then you no longer need to model those each of those paths, which represents a set of behaviors, by the way, set of traces. You no longer need a PC, correct? And that is the key point to observe. Okay, so why, because you are enumerating the path by taking combinations of these branching conditions and modeling each of them individually. Okay, therefore you are doing and you are time stamping them anyway, which you would have done in T. Okay, in a BMC formula, the states in each T is fed from one to the next instance of T anyway. So where that time stamping is happening. Therefore, since you're enumerating it here, you don't need to have PC anymore. Is that clear? Whereas
Ye-
if you, correct? Was that a yes?
Yes, sir.
Yeah, okay. And that is one advantage, okay? And as you can see, each of these exactly captures one way. I mean, each of these three symbolic paths captures exactly one way, one symbolic way in which, that is possible to reach exit from the entry. And these are much formulas that are leaner, okay, than I mean, or at least it is targeted, and that's why it's leaner. Now you can say that the behavior of this program is one of these. It's a disjunction of these three formulas. Once you enumerate the symbolic parts and generate formula characterizing this each in the set of execution runs for each symbolic path. Now you can take a disjunction of these formulas and then claim that that is completely captures all the behavior of this program. Okay, so that was the first idea, even before verification tools like CBMC, which are more popular, and Euclid that came about. And there is a very popular system called CLE that was built based on symbolic executions, and this is how they and the CLE is still in use. It's a tool built by some people in Berkeley who didn't call this a formal verification tool, but they still primarily use symbolic executions and then with optimizations. Okay, so so most sequential verification tools in existence today, the one which are state of the art tools, they go use some notion of symbolic execution to enumerate the symbolic parts and then model them this way. Okay. Yeah, and that is fine. But there is, as I mentioned last time, there is a problem, with this approach, which primarily comes when you have loops in them. Okay, if you try to enumerate this program, uh, then there will be a combinatorial explosion, because if there are like the three-way branching, or a certain number of branching in your body, created by a nested if then else, and each time, and there are n times this loop is iterated, each time there will be three-way branches, so the number of paths will explode. If you try to enumerate all possible paths, it'll be 3 to the n, right? So that may be okay for straight line programs with some limited number of nested if then else's. But when you are trying to do such symbolic path enumerations for loopy programs with loop, your enumeration can get out of hand. The idea is, if you is so, I mean, once again, this represents what the thing is. The idea of symbolic execution is, for loop programs, is you can always do unwinding at the level of while, because after all, in sequential programs, the main unwinding comes as a result of unwinding loops. And so your count k, you would rather have it as a measure of number of times you unwind the loop. And therefore, you could do this way, okay? And then you enumerate the parts, possible conditional parts in the body of the loop. Now, this method is you could be done, yes, but it doesn't scale, that well. Therefore, what tools like CBMC do, they use a certain, I wouldn't call it a trick, but in a certain logical thing, much like Cyton encoding. There is similarity in that thing, so that you don't get, when in combination with loops, you don't get very gratuitous explosion of number of parts. And that idea is what I want to illustrate. Okay. So here, and this notation is called an SSA notation, static single assignment. Okay. So what CBMC does is, it still does unwinding at the level of loop. But the body, any symbolic path in the body, is not enumerated by taking all possible truth combinations of the branching conditions. Instead, what it does is something like this. Okay, it introduces, keeps track of the branching conditions. Okay, so you start with y0 is equal to 1. Say m0 is the initial value of m. Now, suppose, and the condition is m not greater than 1, then each of these is modeled by a time-stamped equation, okay, representing these assignment statements. And at each point, then you have, then M1 is, okay, M1 is greater than M2, that corresponds to line 4, and line 5, this one. And then let's see. So then N1 is Yeah, so all the what is N1? Yeah, and this one is also modeled separately, and Y2 represents the effect of doing this one. So these are the piecemeal thing. And now at each point where the if conditions merge, you introduce a new variable. Okay, a new variable, like for example, in this N2 here merges N1 and 0. Okay. See, N2 says if N naught, which is the N naught is the initial value of N, is greater than or equal to M1, okay, because M1 is the value that the condition on line 6 sees. If that is the case, then it is N1, the latest value of that. Otherwise, it will be the original value. This is what I call as merge points. Okay, there is a merge point merging two ways of getting to this point from this if then else, either directly from 6 to 10 or after executing 8 and 9. And this conditional expression here defines the value of the each variable that are modified in this if then else at this merge point, okay, by introducing a new variable. So y and n are modified here, so there is a new variable for n2, I mean a variable to capture the value of the variable n, a new logical variable n2, a new logical variable y3, which is defined in terms of based on how this condition is true or false. Similarly, you get a merge point here, okay? And for this branching that happens at line 2, and there once again you will see you will merge these two values. If m naught is greater than 1, then you get if this condition is true, then what you have is the effect of whatever M1 is, and similarly, and then you get Y4 and so on. And you can see that by introducing, of course, you're introducing extra variables here, one for every merge point, at every merge point, one for every variable that is modified in those if then else conditions. Okay. So, and that is linear. The number of variables, extra variables that you introduce is linear in the number of branching conditions in the straight line in that block of code. Okay. And so in a way what this is doing is this is a single symbolic path that merges all the three separate symbolic paths that we previously enumerated by taking all possible combinations of the truth values that you can give for these things. So, and where it is here is it is embedded, of course, inside these conditional expressions, but still, as you can see, this is a single linear symbolic path. And now the explosion when in combination. So this is how each body of the while of the loop is translated without enumerating the conditional paths in the body. But at the loop level, you still unwind the loops with the body being modified, I mean, modeled as an SSA. So at least you're partially you're avoiding the explosion caused by the interaction between the conditions, the branching conditions in the body of the loop when it is crossed with the unwinding of the loop. Okay, so that is one crucial kind of optimization that is used in order to control the explosion of the number of parts. Okay. So yeah. So after this, once you model it, the body using SSA, then of course you will have to unwind the K unwinding. I mean the K in the case of unwinding in CBMC definitely, and a lot of the verification tools for sequential program use this SSA notation to arrest the combinatorial explosion that you get in the conditional parts. Yeah. Okay. So is this clear, or do you have any questions here? Are you convinced how you could derive this?
Yes, sir.
Okay. Okay. So what I want to know is, and therefore, when you see in when you do unwinding in CBMC, it is always unwinding and not at the level of the global transition relation, but the unwinding happens at the level of loops. And if they're nested loops, then each of them is unwound the specified number of times, and the body is always represented as an SSA. Okay. Now there is another trick that it uses called unwinding assertions. I will get to that when I illustrate when I start demoing CBMC. Okay, so I want to introduce CBMC here. Okay, and take the next half an hour or so. I intend to go till we started at 6:30, so I want to go till 6:30 to 7:30, 7:45. Okay, 1 hour 15 minutes. So now I'll switch to demoing CBMC, and any questions you have, you can do while. I've uploaded a link to the CBMC the CBMC official CBMC page in the Google Sheet, and that is has all the resources, the tutorial installation instruction for installing CBMC, and the tutorial has quite a few examples. But what I want to do today is to just give you a glimpse of CBMC and some of its basic features. So, any questions before I move to CBMC on um, the SSA notation, or the way unwinding is used? Okay, it'll be probably more clear once I do this. So, what I want to first, that's not what I want. This is the first file that I want to use. Okay, so this program from shown here on line 8 through 15 is exactly the program that for which you saw this SSA encoding here. This is what I have typed here. So I'm going to use that. Okay, CBMC, as the name indicates, it's a bounded model checking tool for ANSI C. Okay, and it is quite widely used in practice. And the reason is it exactly implements ANSI C official semantics. So the input you directly give as a ANSI C program, which is annotated with assumes, like I've shown here on line 36, where you could put assume statements and assert statements. Like the name indicates, assumes make assumptions about the variables. It specifies conditions, constraints on the variables that need to be assumed at the point at which the assume appears. And you can assert is something that you want to check that it holds every time the control reaches that location. Now you could annotate your C program with as many assumes and as many asserts as you want. Okay. Both assume and assert as an argument take a Boolean, a prepositional formula. Okay. Prepositional formula. There's a second argument where, just that's a tag for the assert. Okay. And yeah, that's how it is. And your program is any, standard ANSI C program. And you can, yeah, I mean, almost all 100% features of ANSI C is covered. And that's why it is so popular. You can just take this, any program, and you can start putting assertions and start verifying it. So let's see. So here I'm claiming in that program y at the exit point, y should be greater than or equal to 0. So I've defined various variables in here, including the ones that are used in this fragment of code. So do you expect y to be greater than or equal to 0 when you execute this program at line 15? Should this assertion pass or fail?
Sir, can you please zoom in?
Sure.
You want me to make it bigger?
Yes, sir.
Is it better? Is it better?
Yes, sir. Yes.
Sir, are we assuming anything about X?
No, this is exactly ANSI C. When you define something in here, these are not global variables, right?
Uh,
So ANSI C semantics says that if it's a global variable, then it initializes to 0. Otherwise, it is left uninitialized. Therefore, yeah, so X could be anything.
But x should be greater than equals 0, right? Because it's an unsigned int.
That is right.
So it should pass then.
Okay, let's see if it does. Yeah, the way you include, yeah, I'll just show a few. So you need to, once you define something, you need to compile it. And this compilation step really does generate SSA and then does, and represents this program mainly as an SSA program. So, I mean, of course, I have defined lots of different things in here, a lot of asserts and so on. Show properties will, yeah, it shows all the asserts, okay, that are defined in the program. So, and then you have to pick. If you just run CBMC on the thing, it'll start verifying each assertion in your file one at a time. But if you want to verify one particular assertion, you just have to do this. And then, and since I want to do check the assertion on line 15, that is named as main.assertion.1. Therefore, I do this. Okay. Now there is another thing that you can, I mean, if when you verify a particular, check a particular property, you can name the property. And either when you do that, it already, I mean, obviously does BMC, where the unwinding depth is not at the transition relation level, but rather at the loop level, which is what makes more sense for the thing. That is what it does. I mean, in this case, this is a straight line program, so unwinding doesn't make there's no unwinding needed. So, it checks it, and if it fails, it gives up. If it succeeds, it just says verification successful. Otherwise, if it fails, it gives a witness to the error, and you can get that by asking for a trace. Okay, let me check that. You see, it failed. Okay, there is a subtle thing about here. See, y I have defined as an integer. Okay, x is an unsigned integer. I don't know if how many of you know. I mean, C has this very complicated typecasting rules. Okay, so if x is an unsigned integer, now I'm assigning y here on line 13 to a result of multiplying x times y. So there is some casting that goes on from unsigned to int, okay? And that throws a monkey's wrench, okay? So as you can see, it is giving that input value for which this thing condition fails. Okay, this is an unsigned integer use represents, and this is like one unsigned integer can have a one here in that 32-bit thing. I think this is 32-bit thing it is using. So, but this, when it converts it into an integer, it treats it as this sign bit, okay? And treats that becomes minus this, okay? And with y being 0, and that is incremented y is 0, then y becomes 1 here, it's initialized, okay? And therefore, it can become negative, yeah, because of that conversion thing, yeah. So you see, if these kinds of subtle typecasting, etc., are all can create issues. Okay, yeah. So do you understand this? Where the error is coming from?
Yes, sir. So this tool can be only used for ANSI C, right? Then I mean,
Of
because
course,
it
it's meant as a
okay,
C
okay.
Bowdle model checker for C, yeah. But it covers 100% of ANSI C, all features, pointers, anything you want. Okay. And actually, it
Okay,
works for C11 multi-threaded programs as well. Okay, there's a version of CBMC that runs for multi-thread. But the important thing is that no feature is no subsetting of ANSI C, actual ANSI C complete with all typecasting, everything. Yeah.
Yes.
So let me now. So this is the formula representation. If you want to see how this program with the assertions, etc., is represented, you use this. Yeah. So this is the formula that is actually shipped to Z3 or whichever way. CBMC can has multiple, gives you options as to which backend engine SAT solvers, SMT solver that you have to use. Z3 is also an option. There's Boolector, and there's something called MathSat. Okay, you can use any one of them by choosing at installation time, I think. So you should read this formula as if all the conditions above the horizontal line, a conjunction of all the conditions above the horizontal line implies what is below the horizontal line. This kind of annotation is called sequent. It's called a sequent. That is, the formulas minus conjunction of formulas from -1 to -23 implies this. Okay. Now ignore all the things that are stated from -1 to -11. They are some thread initializations, etc., etc. And so, as you can see, there is a little bit of, I mean, the variables are time stamped. It starts with y0. No, no. Yeah, the last one following hash is the actual value. Now, why it starts with 2, it's a bit puzzling, but nonetheless, I think it starts with it gives some initial value as soon as it is declared. Yeah, maybe the declaration itself gives number one, and number two is the from where you start off with your explicit assignment. Okay, so in any case, what you have to see is the first bit, the first thing of at one, etc., is for the thread, I think. So your timestamps is what the number that follows hash. Okay. So at this point in line 8, y is, y takes a new value, and y, that is y2, it's equal to 1. And then as you can see, it defines the guard at 9, okay, in terms of, no, the guard, this, yeah, guard m is defined, m is greater than or equal to, this is defined as the, guard 1 is defined as greater than or equal to 2. And these are the individual assignments. Guard 2 is defined as n greater than or equal to m. Yeah, the greater than 1 is the same as greater than or equal to 2. And then it assigns all these things. And then you see it does create merge points. Okay. Merge points -19, -10, -20, etc. They're all merge points by introducing new merge variables for n, m, and y. Okay. And so that's all. This is exactly what is here from -12 to -23 is the SSA notation for SSA encoding of the code from line 8 to line 14. And after that, it does the assert is what you want to ensure at line 15, and therefore this what is in the Boolean expression in the assertion is instantiated on the latest timestamp. Okay, y on y at 6. Okay, timestamp 6, because it introduces additional variables for each of the merge points. The latest timestamp correspond of y is 6, and it checks if y it asserts that y must be greater than or equal to 0, assuming all the SSA. So what is shipped to SMT solver is the negation of this. Okay, I mean, this implies negation of the assertion, and so any SAT instance will give you a violation of the thing. Yeah. Okay. So next example I want to do is, yeah, any questions here? You can start exploring. I just want to give a little bit of a teaser, okay, and then relate it to the theoretical part that I've actually covered. And once you get acquainted with this, you will have to you can run with it. Any questions?
Uh, yes, it seems a little bit unsettling to me that in a way that we made the value of x so large that the C interpreter interpreted as like negative number. Is there any way to get like around this?
No, 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 no. See, well, you said it's a bit strange, or you used a different adjective. I made the assert statement. Now you have to fix the program. So that's why I asked you what the expected behavior is. Okay. And it was not obvious that there exists a value of x for which this expected behavior is not true. Okay. If this is what your expected behavior is, then you should have constrained the input to x. I mean, the input value of x. Okay. Either by specifying some assumptions on x or initializing x appropriately. Correct? Why is it unsettling? I feel it's liberating.
Hmm.
It's liberating in the sense you wrote the code, you're writing the specification, which according to your understanding is what is expected. Either the way you wrote what the expected, the assertion is wrong, okay, which is possible, but assuming that your specification is correct, I mean, usually it should have been your responsibility to have initialized X properly. No,
Right, yes.
that is what is the thing. So view all these verification tools, including CBMC, as a stubborn uh, critic or stubborn, doubter, okay, of your thing. It never believes that this assertion is correct. It always tries to find if there exists a behavior, okay, acceptable behavior as per ANSI semantics that can be made to violate your expected behavior. Okay, it looks at all nooks and crannies, all possible values that it did. Of course, it is not checking for each value by running it. Okay, that's where the symbolic encoding matters. Yeah, so it is converting that into a formula. That is why it's called VCC. VCC stands for verification condition. If this thing is violated, if this formula that is shown is violated, that is, if the validity of this formula is violated, then there is an error. Okay. Yeah. Anyway, so I'm saying that it is, yeah, it is not, it is unsettling for you because you made something wrong. Nah? Okay. But X is, that value that it gave is an acceptable value as per this program. Nah? Yeah. It's in that sense, I say it's liberating. Okay. Any other questions? Let me then take a loop program. Yeah. This is a very silly loop program. So I'm assuming, so I want to illustrate what assumptions we can make. I'm assuming X is between 98 and 99 inclusive. Okay. And I want to check if this assertion, must be true, correct? Do you believe? Anyone?
Yes, yes.
Okay. Now, here is a loop program. Now, since CBMC is a bounded model checker, I mean, for loop programs with loops, you will have to unwind them, okay, and make it generate. Unwinding is the method that is used to generate these symbolic paths in SSA notation. So You will have to. Okay, first let me. There's only one thing here. Okay. Let me try to verify that. Yeah, I'm sorry. I hope you can read the terminal window. I don't know if I can increase the. Not sure. Okay. Yeah, if you try to run this without specifying any unwinding, it'll assume unwinding. It'll unwind forever. Okay. In this case, it's okay to unwind, but you can always specify a specific value of unwind. Okay. Oh, yeah. See, this is the yeah. So it keeps unwinding. So you will have to specify some unwind depth, otherwise it'll. Oh. So if I did unwind, say 1, what do you expect would happen?
Just one branch, just one depth one.
No, I'm asking you what would be the result? Will it check? Will it say success, failed?
Not sure.
Why? Yeah, anybody else? See, the question is
If
for,
it started
yeah,
from 99, then I think it's set. So it might
yeah,
say
if
it's
it is between, yes, the question is for the permissible input values, in this case, X, is there a way with unwinding 1 to reach the exit point, which in this case, where the assert is placed, 9. Okay. There is, I guess, nah? So what it'll do is it'll say verification successful. Okay. Now it would say here, when you interpret this, in this case, it is indeed successful, because when x is equal, see, if x is equal to 99, then after one unwinding, it does get in here, and x is incremented by 1, and therefore x is indeed 100. Yeah. So it passes. What if I changed this one 98 and then ran it? What would you think it would say? Let's try to run it. Yeah, isn't this puzzling? Okay. What happened here? If x is equal to 98, one iteration is not adequate for it to even reach 9, correct? Do you agree? Anyone disagree?
Yes, sir.
Therefore, it is vacuously true. If you never reach the point at which, okay, so whenever you place an assert statement in a sequential program like this, what you're trying to verify is for all the traces that it generates, okay, that globally, if you view it as a global, it is G of something like this is what you're trying to show. If PC is equal to 9, then X equals 100, something like this, okay? Yeah. So the G here means that every time for every trace. But now the trace never reaches this point, and therefore, if it never reaches PC is equal to 9, never happens. Correct? Therefore, this is vacuously true because the precondition is always false. Yeah. So if for those programs that are non-terminating, or if your unwinding depth is inadequate, for it to even get to reach this assertion, it'll be vacuously true. Okay, so you have to be careful in the way that you use this thing. So, if the unwinding depth is inadequate, then it may say false because it never thinks. So, what is a way to protect against this thing? Okay, and in general, it is hard to find. In this case, you know for any given value of x what the unwind depth is. You can clearly calculate and you can enumerate it. But if in a complicated program you don't know what it is, and therefore CBMC gives a very clever feature to see if your unwinding depth is adequate or not. Okay, and that is I do unwind. I think it is unwinding research. Let's see. Yeah. See now what it did. Okay. Yeah. See, implicitly what it does is it implicitly puts an additional assertion. At the end of this unwinding, it checks at the exit point if it is ever possible, if the negation, okay, of this loop condition is possible, okay? If not, then it knows, because there are cases where it, uh, the loop condition is still yet to, there's no exit. There are there is still, okay, it checks if the negation of the condition, I mean, if that condition holds good, if it is still possible, if it is not, then it says, since there is still, there are situations where you can have a value of x, from value of x in the thing, for the thing where it can get, x becomes 99 here, and it knows that there is a way to, there is more unwinding that could be done. So it does, after those specified number of unwindings, there is an implicit check that it checks if your loop condition, exit condition is can be is still is false, then it says, there is not enough unwinding, and that unwinding assertion is what has failed here, as it has indicated, you see, unwinding assertion failure, which means that you can see that's verification successful is kind of a spurious or a vacuous condition, that it happened because it has not exited the loop at all. So this can be used. About 5 minutes before it. Okay. Yeah. So is that clear? Yeah. So you can use this feature to see if your unwinding is adequate, or if the reason that it is saying successful is because for that given unwinding, for all the possible input values, you never were able to reach the exit point, and therefore it is vacuously true. So that also gives an indication, A, that there is more unwinding that you need to, do. Yeah, the adequate or not. Okay. Maybe this is a good point to stop. I have a lot more examples. Oh, let me see what the VCC is like. Okay. Yeah. See, with unwinding assertions, there are two things that it has to show. One is, this is the SSA generates the SSA corresponding to once it unwinds the specified number of times, it is enumerating an execution path, a single symbolic execution path, correct? Or no, I mean, for each unwinding, there is one path, and it takes the kind of the disjunction of those paths. Each unwinding results in a symbolic execution for which there is an SSA, and there will be or of that. Okay. So, and in this case, there was only one unwinding, and therefore this is the thing. And then it says that if you exit, if the guard one, if guard one, which is the loop condition, is false, then your assertion must be true. In this case, it so happens that guard one uh, is vacuously false. And then you see, it says it also checks if there is if not of guard one is can be true at the exit points. It can never be not of guard one can never be true. I mean, it's never true, and therefore it shows that it never exited, and therefore that indicates that your unwinding depth is not adequate. Okay, so you can now see, increase it to 2 and see what happens. So even here it fails, because here it actually requires 3 unwindings, because as you can see in the while loop, it has to go through for huh? Yeah, 98, 99, and there is always also a check for after it increments from 99 to 100, and that's when it exits the loop. And therefore, you actually need 3 unwindings to get this thing. Yeah, uh, yeah, and so on. So I think yeah, maybe it's still, we start at 6:30, so I have a few more minutes. If you can allow me to do so, a few things one thing that I want to illustrate, okay? Any questions there? Now, yeah. Now, you see, there is one when you start using CBMC, like I've been um, making a point throughout the course to say the power of non-determinism. Okay, so non-determinism is a very powerful and useful tool, both in specification as well as modeling. Okay, so we are already seeing non-determinism. So when you define uninitialized variables here, it means that your input, those things can take any value. And as you see, there was a problem here in this program. Or explicitly, you can use the thing. So suppose I assert I is equal to 0 here. Is that true? Since I is uninitialized, it could be anything, so this will be false. Similarly, I is equal to j. Is that true? No, because I and j both uninitialized, they can be two distinct values. But there is a way that you can actually make them somewhat. I mean, when you do assume something like this, I is between 0 and length. This is what I call as a non-deterministic assignment. You're already imposing, you're not giving any specific value, assigning any specific value to I at this point, but you're only specifying some constraints. Okay. And this is a very powerful tool. So for example, after I do this, is this true? The one on line 99? Okay. I mean, here you'll have to be, these kinds of things you can make. You can make arbitrary assumptions. Okay, so here, okay, let me go one by one step at a time. So here I'm assigning I and j. This is another way. You can either leave I and j uninitialized, or if you can explicitly assign them to some function. Here I call it non-det uint, whose body is never defined. It's a function that returns a uint. That body is never defined, so which is equivalent to saying I is being assigned to some arbitrary non-deterministic uint, and j to some other non-deterministic uint. Okay, then if you're assigning a, I, and j to arbitrary values, is this true? After that, anyone?
But that ing might not get assigned the same value. So
Correct. Okay. So that's why it's false, because I and j, while each of them is arbitrary, there's no a guarantee. I mean, there's no need that they have to be the same thing. Now, when you do assumes, so you'll have to be a little bit careful. Okay. Here I'm assigning I is equal to length plus 1, where length is a defined constant 4. So after this assignment, it is 5. Okay. So length is 5. Now, if I do something like this,
then it is definitely false.
yeah. So here you are, the actual value of after the assignment on line 35 is contradicting this assumed. Okay. So, so it's what the SSA that is generated is just the SSA for each of the individual statements. And can someone mute their thing? This background noise? Yeah. Oh, thank you. Yeah. So yeah, when you make assumptions, you will have to make sure that they are consistent with the previous assertions and the assignments that are made. So you can't make. I mean, it's good to have us assumes now and then to constrain your search space, the verification space that you're trying to explore, and it's a good tool for specifying input assumptions. But you will have to be careful as well. Okay, and and once you make such inconsistent thing, because it is false, false implies anything. Therefore, all assertions that you make after the first point at which you introduce an inconsistency, they all become vacuously true. So you have to be careful, okay? When you're having lots of assumptions and asserts, you will have to make sure that your assumptions at every point, the conjunction of all the assumptions that you made up to that point, is not introducing any inconsistency, okay? And yeah, that is something that you have to do. But there is always a way that you can actually check. This thing is I deliberately try to verify, see if I can verify false. Okay. So after this, if you try to verify false, you will see it will be true. Okay. Because this can never be true. If we want to check if after I make an assumption that I haven't introduced any inconsistency, one clever way to do it is to have an assert zero at that point. And if that assert zero ends up getting checked successfully, aha, then an alarm bell has to ring. Okay, some set of assumptions that have introduced is those are inconsistent, and therefore you'll have to debug them in your. That is like debugging your specification. Okay. Yeah. No, I will just show you one last thing, and I will end my thing here. Just to show the power of non-determinism. I have two assumptions here. Okay. Assumption on line 6 says Z is between 1 and 4, inclusive of the limits. Okay. 1 and 4. I is some unsigned integer. What exactly does this assumption mean? By the way, I less than less, I'm sorry, this should be 1. This means that,
Z2 to the
Power
power.
n.
yeah, okay. What? Say that again.
2 to the power I. Z
Yeah,
equals to 2 to the power I.
that's right. Are the rest of you convinced? Okay. So this says that Z has to be, yeah, some power of n because I'm shifting 1 to the left. This is bit vector shift. Okay, since every integer, unsigned integer, everything is represented in C as bit vectors, this actually means that if I shift it by some I, where I is some non-deterministic integer, then it has to be 1. So when I shift this by a certain amount, it is what you get on the right side here will always be a power of 2. So this is a very succinct way of saying, making an assumption that there exists an I, because I is left. Whenever you do assumptions and with some I being unconstrained or some set of variables unconstrained, what it says is there exists an I such that uh, Z and I should, there exists an I and Z such that this should hold good. So the value that's Z and I is completely unconstrained. So here it is, has the effect of constraining Z, and you should interpret. So these kinds of assumptions, if you have some variables kind of free and unconstrained, it has the effect that there exists something such that that constraint holds good. And that's what is being exploited here to specify that I want to constrain my Z to be a power of 2. This is one way to, one succinct way to do using the things. And obviously, it cannot be 0 because it has to be power of 2. If you try to check this, this should get violated. Okay. So I just wanted to introduce you this power of non-determinism that you can actually use, and in some limited way, although explicitly both in assumptions and an assert, it only is what you can specify is purely formulas in propositional logic. There is a way that you can get a limited amount of quantification, quantification expressibility, when you combine non-determinism. That is the key point that I wanted to illustrate here. Okay, so you get kind of existential quantification in assumptions, and you can use non-determinism to get for free universal, the expressibility of universal quantification in your assertions. And I will show you how next time when I continue this CBMC demo. Okay, I'm going to stop here. And I know it's been no, I said I'll go till 7:45, but I've ended up early. Are there any questions so far? Okay. If not, then I'll see you next Tuesday. We agreed Tuesday, Thursdays, correct? So the next class will be next Tuesday. Thank you for showing up.
Thank you, sir.
Okay.